Pessoal, eu vou, antes de iniciar aqui, eu vejo que o Dr. William Dupps já está aqui conosco, bem com o Vinícius. Antes de passar para o inglês, eu vou só avisar a todos que hoje será uma sessão muito especial. Nosso tema de hoje será a biomecânica da córnea. E nós contaremos com um painel aqui composto por mega especialistas no assunto. Eu acho que é uma honra ter uma discussão, promover alguma coisa de tão alto nível dentro aqui da nossa reunião. Então, de antemão, já agradeço a todos. Logo, então, vamos começar aqui em inglês. So, good morning, everyone. Good morning, Professor Dupps, and also Vinicius is already with us. And first of all, I'd like to thank for your participation. And as I was stating before in Portuguese, this is a very special meeting for us because we are able to get together some of the very, very best specialists in this area. And it's, of course, a very high level group that we could put together here. And it's really a pleasure and an honor to be with all of you today. So without further ado, I would like to ask Vinicius if he could share his screen, and thank you once again for your participation. Vinicius will start with his lecture on basic concepts of corneal biomechanics. So Vinicius, please.
Okay, good. So, good morning, everyone. It's a pleasure to talk to you guys again and to talk to Dr. Dupes as well, my mentor, my PhD, one of my PhD mentors. And this topic is always something that it's kind of hard to understand sometimes, kind of misunderstood a lot of times. And it's a pleasure to speak to you guys about corneal biomechanics. So, we'll start with this lecture will touch base on a lot of basic concepts. I will not talk a lot about many clinical aspects of it. I'll let the other speakers mention the more clinical stuff. This is really about basic concepts and stuff that we all need to know before we start discussing and when we read articles about biomechanics. So bear with me, because especially in the beginning, this will be a little bit tough. So this is just, it's not Thursday, but this is like a throwback Friday. And this is from picture from our research team when I was in Cleveland doing my doctorate study, and Dr. Droops here on the left. This is Ibrahim 7. He's and this is Matt Ford. They are both engineers, and we all work together with Oct Elastography a lot. And this is pretty much the research team in which we published a few papers about Oct Elastography. So always bring good memories when I see those pictures. So what is biomechanics? So biomechanics is the study of mechanical interactions of solids or fluids with internal and external forces in the context of biology. And this is what we're studying, right? So we are studying the interactions. That's I think one of the major things that we need to understand. Like whenever we measure biomechanics features of any tissue, we have to disturb it somehow, either by light, either by force, either by ultrasound. There needs to be some kind of interaction so we can analyze its response. And in medicine, we've been using biomechanics in many different areas, like in orthopedic surgery, cardiology, anywhere that involves like prosthetic devices. So again, orthopedics, prosthetic valves. So they all have their own like biomechanics studies and lines of study, and it's been in medicine for a long time. And not for ophthalmology, not only for the cornea, not only for refractive surgery, but also for glaucoma. It's probably the other major area where biomechanics is implied. So there's great interest in trying to understand how this sclera biomechanics work, how trabecular meshwork works, optic nerve head, specifically the cribriform layer. So it's a lot of research in that area. try to comprehend how glaucoma develops and how it progresses as well. And of course, we're going to focus here on the cornea to talk about ectasia and refractive surgery screening. So when we talk about refractive surgery and biomechanics, the major question is always like, is this keratoconus or not, right? Like, all our measurements today are based on either the clinical exam, topography exams, tomography nowadays most used. And we all have faced situations where we see a cornea with a inferior steepening, but the thickness is not that bad. The anterior and posterior elevation maps don't show any major red flags, and we don't know exactly what to do. But then we rely on other indices to try to help us. So we have scoring systems like the Random score. We have countless indexes that all have been described to try to find something that would describe this patient as a suspect or a not suspect. So, and we know that if either of those letters here were really accurate, probably neither of the other ones would exist, right? So, or even be remembered. So it's a lot of stuff to remember for just one patient sometimes, or just one case. So that's why we study biomechanics. We want to go to the root cause of the issue, right? We want to analyze if that cornea is strong enough to have surgery or not, or is it weak enough that it's progressing or not in terms of keratoconus. So that's why we study biomechanics. And when we talk about biomechanics, the major concepts that you have to have in mind are those of stress and strain. So what is stress and what is strain? So again, bear with me here, okay? Stress is whenever you are getting a tissue, a solid, whatever you're using as your object of study. Stress is the force that you apply in a specific direction divided by the cross-section area of that device. So let's use the cylinder here as an example. The force is on this vertical direction here, and the area is the cross-section of the cylinder here, which is the circle, right? So that's the definition of stress. And remember that this has a direction, right? So we're measuring stress in this direction here. Okay, this is important for what's coming up. And the strain is similar. The concept is similar to deformation, or a potential of deformation. Let's put it this way, which is basically the difference in size. So the elongation that stress causes, right? So this is the final length of this cylinder divided by the initial length. So it's the difference that you created divided by the initial. So strain is an eight-dimensional constant. You're dividing length by length. So you don't have a unit here, right? So why is this important? Because whenever you divide stress by strain, you have the so-called Young's modulus or elastic modulus, and this is the main, this is the holy grail of corneal biomechanics, or biomechanics, to be honest, because that's the number that we're all trying to find. Like, is the cornea stiff enough? Is the cornea weak enough? This is the variable that we're all looking for, and that all major biomechanics study will try to report, because they will divide the stress over strain, find the tissue property in terms of elasticity. Now, this beautiful linear curve here, we're only talking about linear elasticity. When we are talking about the cornea is, and any other biological tissue for that matter, is nonlinear. It responds to stress in a nonlinear way. So what does that mean? When the cornea is stretched, the collagen fibers that we have within the cornea, they are recruited one by one. So initially, when the cornea is not under a lot of stress, it takes just a little bit of force to cause more deformation. As you keep stretching the cornea, you need more force to cause just a little bit of deformation. So the cornea stress strain curve tends to have this shape here, meaning that the more stress you have, the less strain you cause. So at some point, this will break, and then we have what we'll call the breakup point. I won't go there, but this is basically what the stress strain curve for the cornea is. And to be honest, this is for almost every biological tissue. I'm going to mention a couple other variables here because they are important and they are reported in many biomechanics study. But one of them is shear modulus, and shear modulus is like in most formulas, this is the letter G, and I won't go a lot in here, but just to understand, think about a dull scissor, right? When you're trying to cut paper with a scissor that is dull. So you have two forces acting in parallel, okay? So in this cube here, you have the force pulling this cube to the right, but you also have friction that is preventing the cube to move. So you cause deformation in this direction. Makes sense? So this is what we call shear modulus, and you have a formula that will analyze this. Why this is important? Because in the cornea you also have this horizontal strain that happens every now and then. The cornea is a circle. Is like if you want to simplify it, it's like a sphere. So you have multiple loads, multiple stresses coming from all different areas. So you cannot define the cornea only by Young's modulus. You have also shear modulus. And you also have something called Poisson's ratio, which is a ratio, as the name implies, which is basically divides the lateral over the longitudinal strain. So it's basically measuring how that tissue, how that shape deforms when you apply a stress. Why is this all important? Because in the end, all those major variables, E is the Young's modulus, G is the shear modulus, and V is the Poisson's ratio. They are all, you can kind of derive one from the other. Poisson's ratio for the cornea is usually defined as about 0.45, 0.49, depending on the study that you see. So pretty much if you have a shear modulus, you can calculate Young's modulus and vice versa. So they are all related. Now, this formula is true for perfect elastic tissues or materials, right? Again, it's already told that the cornea is not perfectly elastic, but sometimes when you're measuring just one point in the cornea or just one point in any biological tissue, you have to make some simplifications. So that's why we use that. It's important to know that. The cornea has also another property called viscoelasticity. And viscoelasticity basically implies time. What does that mean is that if you keep the stress level constant for a determined period of time, the strain will slow, it will start, you will have some deformation initially, and then it will reach a plateau. Or if you keep the strain constant, the stress within that tissue will basically fade over time as well. And that's usually what viscoelasticity means. So whenever we talk about viscoelasticity, it means how the tissue changes, the stress-strain relation changes over time. Again, this is also important when you think about all the studies, especially in ex vivo studies, that you cannot keep tissue stretched for too long, otherwise you're having a lot of viscoelasticity implications there. And hysteresis is another concept, another term from physics that is basically the loss of energy that you have when you're deforming a tissue, that it will, whenever you release stress, you will respond differently from when you were applying the stress. So the loading phase of the stress strain curve is different from this unloading phase from the stress strain turn, and this dissipation of energy, the area under the curve here is when you calculate hysteresis. So this is a little bit more complex than what the aura says, or maybe most of you have used or at least know the aura, in which they use hysteresis or corneal hysteresis as a simple like pressure difference from when the cornea is applanated in the loading phase of the air puff and then the unloading phase of the air puff. The idea is similar, but it's not exactly the same, right? So just keep that in mind. That's the true definition of hysteresis right here, okay? Well, we all know that the cornea, from a from its perspective, from its structural perspective, it's highly dependent on its structure to have adequate function. And from a material science standpoint, the cornea is called a complex anisotropic composite. So the anisotropic part means that it will respond to stress differently depending on where that stress is coming from. And as I said before, the behavior of this tissue is nonlinear, elastic, and also has viscoelastic properties. So since the cornea is so complex, it will have regional differences when you try to study biomechanics in different parts of the cornea. So the collagen fiber orientation is a major drive for that. So the collagen fiber orientation in the center of the cornea is pretty much orthogonal. So this is an X-ray scattering study from Dr. Meek. It's referenced multiple times in many studies, in which they analyze how the collagen fiber is orientated across the cornea. And in the center, as you can see here, it's pretty much like a cross, right? They are all like coming either in vertical or horizontal directions. And in the limbus, it's circular. The orientation changes as you move to the periphery. This is one explanation. I mean, there are many others, but this is one of the major differences why, if you want to apply this in clinically or surgically, why an AK or an LRI causes much less biomechanical disturbance compared to an RK. Because the RK, you're crossing all the way from the periphery all the way to the center. So you're disrupting those fibers, especially in the periphery here, in orthogonal to its direction. And in an AK and an LRI, you're following the direction of most collagen fibers here. So that the entire cornea disturbance from that incision is much less compared to an RK. And when you measure anterior to posterior, there is also great differences. So the collagen density and the way the lamella, the collagen fibers are structured is strikingly different from the anterior segment of the cornea compared to the posterior. So you can see that in the anterior part, there's higher collagen density, and there is a lot of interweaving between those fibers, and also most of them are anchoring at the Bowman's layer. And in the posterior cornea, this interweaving is less. The corneas are more like stacked, and that tends to have less resistance to any disturbance. So this is why the anterior segment of the cornea is the one that is responsible for most of its tensile strength, because of this is the way these collagen fibers are structured. Okay, this is why we have what we have. So when we are studying biomechanics in the lab, extensiometry is still the major method to study any tissue, because you can directly measure Young's modulus. So you're literally stretching the piece of tissue that you have, and you measure the strength, you measure, the stress, you measure the strain that you're causing, you have the Young's modulus of that tissue. And the reported values vary anywhere between 0.5 to 5 megapascals. And the reason for that difference is because there are some stress and strain preconditioning of that tissue before they actually measure, and depending on how the preconditioning is made by that study specifically, that can change the results a little bit. So the most of the studies with extensiometry have found that difference that I was mentioning before, that you have an increased Young's modulus at higher level of stress. And then we have inflation tests. This is another lot used method to analyze biomechanics in the lab, where you use either the whole eye or you use an artificial anterior chamber. It's less destructive than extensiometry because you can mount the entire cornea there. It's more similar to physiological stress and strain, because if you think about how the tissue is, how our corneas right now are under stress from IOP, for instance, this is more similar to that. And you can also measure other types of strain, not only the axial strength, but also the circumferential strain, the meridional strain. So remember, as I said before, that the stress and strain, they have direction. So you can measure that with the inflation tests, but being a multi-directional load and multi-directional strain, it increases the complexity of the analysis of this data by a ton. So you need way more advanced techniques to mathematically calculate your findings. So this involves much more, it's not a simple division as extensiometry most of the time tends to be. And then finally, when we talk about in vivo assessment of biomechanics, we all have the earpuff devices. This is the Aura and this is the Corvus. We learned a lot from them, but They are air puffs, so they're causing a big disturbance in the cornea to try to see how it responds. And especially with the core viz, we have lots of variables that we can analyze, and they give a lot of insight in many cases. We have optical coherence elastography, and this is a technology that I have worked a little bit more with Dr. Jupes, in which we're, at the time that I was there, we were applying this lens to literally applanate the cornea and measure how that cornea was going to dislocate. This is my cornea, by the way. We were measuring how that cornea was responding to that applanation force. And of course, we had force sensors and everything to analyze that. We also have phase decorrelation OCT. This is also another work involving OCT by Dr. Jupes. I worked briefly with that as well. But phase decorrelation OCT is basically a light scattering method. So you measure particle motions within the tissue. And there is a theory that if you get two pictures at two different times, you can measure how that particle is moving or losing its movement, and that's directly correlated with viscoelasticity properties. And from that, you can derive many other elastic properties. So just to put it in a very, very, very summarized way, and that's what phase decorrelation OCT is. And Dr. Jupes has published a few studies about that. And I hope he talks to us about that a lot today. And then we have brilliant optical microscopy, which is another light scattering technique. So here, instead of the phase correlation, instead compared to the phase correlation, what you're measuring here is the brilliant shift, and the brilliant shift is based on how light changes when it's when a photon impacts a tissue. It causes the light to be scattered. It changes its frequency. This frequency shift is directly correlated with the elastic properties of the tissue, and that's what brilliant microscopy measures. So it measures that frequency shift of the photon, and that's directly correlated with the elastic modulus of the tissue, and that's why you can also get depth dependent, just like phase decorrelation OCT can get depth dependent elastic properties of the cornea. So if you want to divide those four major areas here, you have the perturbatory methods, either by an air puff or by direct contact, or you can have the non-perturbatory methods, which is basically you're using just light to assess the biomechanics. And in summary, so understanding corneal biomechanics is crucial to try to better assess common diagnostic challenges. The Young's modulus is the main variable that analyzes the stiffness of a given tissue. The extensiometry and inflation tests, they are still the gold standard techniques to measure biomechanics ex vivo. And also all those experimental methods that I just mentioned, they are available to assess corneal biomechanics in vivo. Of course, we know that the core viz is available, widely available, but the other ones are still in development, or at least like have just a few sites that have them. So hopefully they'll be available to all of us very, very soon. So thank you all. I'm open to questions, and then that's it. Here's my contact information. If you guys need anything, have any questions, feel free to shoot an email. Okay, thank you.
Congratulations, Vinicius, such a fantastic lecture. Your talk was a way of demystifying, as you said, such a complicated topic, and it will certainly help us to discuss it now. And now I would like to introduce our participants in this roundtable today. And as I've stated before, it's an honor to be in such a group of such high-profile researchers and specialists in this area. And Vinicius was the first one to talk here, and he's a former fellow of this house, and it's always a pleasure to have you participating in these meetings and now in such high level. And Vinicius has accomplished his graduation, residency, and doctorate here in Escola Paulista de Medicina, and then he moved on to the United States in Cleveland Clinic, and now a resident in Nebraska Medical Center. And he was at Cleveland Clinic with Professor William Dubs. He has an educational career and academic career, an outstanding academic career with close relationship with translational medicine, and a specialist in corneal and refractive surgery, director of Cold Eye Institute of Cornea and Refractive Surgery Training Program at Cleveland Clinic, and is a pleasure to have you here with us. Thank you very much, Dr. William Dubs. And also Dr. Dmitry Cherniak, he's president and CEO at Intelon Optics, has a large experience in R&D in industry and patents related to breathing microscopy. I hope he can disclose some of the details on his projects here today, and we'll certainly bring up some news about it. And also Professor Renato Ambrosio, also a colleague here. He has an extensive line of research, mainly in tomography and biomechanics, and he's already been with us sometimes here and in these meetings, and is always honored to count on you for these talks. And he's the actual president of the ISRS, and with such a phenomenal team, we're gonna start, and this is all gonna be coordinated by our Professor Paulo Shore. And I'll now pass on to Paulo Shore so he can start this great roundtable. I'm certain that it will be wonderful for all of us. So please, Professor.
Good. So we are not the coordinators here. You are the coordinator. Like Wallace said, you were the major star here as Vinicius. So the young guys, we kind of accomplished our mission to keep the ball running, and we are sure me, Wallace, Balton, Mauro, that are here as professor of the Department of Ophthalmology, that you are taking a much better care than we could take in our time. But it's a pleasure to be here. It's a pleasure to receive our former students as Vinicius and our longtime friends and also professors as Renato, BJ Dupes, and Dimitri. We have a very long time relationship with you all, sent nice students to you, receive you here with very good pleasure, and hope to have you here again and again and again, and visit you either in Arvo with short sleeves and shorts. Hope that time will come back again, right, BJ? And visit Dimitri at Intelon, try to talk with Luis again, and surely Renato is closer to us, but also to be able to visit the beautiful Rio that he uses to place as his background pictures. We will have a short time of discussion after each presentation, so we can make a quick fire, as Felipe said. We have time for one question now, and then we will go ahead with BJ Dupes. Very nice talk that Vinicius said. By the way, Vinicius, very nice presentation of yours. That Vinicius said is a non-disturbant technique that BJ will try to prove to us that the light won't disturb anything. So your theory is that it's a non-disturbant thing because of what? I'm just teasing. So we have time for one question. If anyone wants to ask, let me check here. Yeah, you're just great talk. So I have a question for Vinicius. Vinicius, we are trying to understand the cornea itself, isolating each property and trying to put all the things together. So the idea as doctors, as we all are, we know that the things are not as clear as the mathematicians think they are.
Yep.
And in the end, we want to be shown something that we cannot see by our eyes. What's your idea on that? What can we already see beforehand that we are not seeing by our eyes? And I will keep asking this question from the beginning to the end, because it's my duty here to challenge all of you and to ask, well, I can see things. What else are you showing me that I cannot see? How can I predict something based on basic models or basic concepts of science? It's a philosophical question.
Yeah, it's a very good question. It's well, it's very hard to see that, right? I mean, what we see now. It's with Pentacam, with the Corvis, with any tomography that we have, we see the final result of that biomechanical disturbance, right? That maybe, let's say a patient has keratoconus, we're seeing the end result of that. What we can measure today, to either predict that or to stratify it, with mostly readily available right now with the Corvis, and I'm pretty sure Dr. Ambrose will talk a lot about that. But what we can measure today is today in clinic, we can measure how the cornea is responding to an air puff, right? What most of the research has been most of the recent research has tried to do is try to understand exactly how we can infer some of this, how that disturbance can affect the entire and regionally the entire cornea. So a lot of the ways that we use to analyze this involves you have to have like a computerized model of the cornea to try to. You can't see that in vivo yet, and honestly, I don't know if we ever will completely. But we will always need to have some kind of like computational modeling with it to try to see how the cornea itself will respond in the stroma, in the many layers of the stroma, but also how the whole eye interacts with that tissue as well. So I don't know exactly how much we can see yet about that. Again, the most readily available device is the Corvis, and it has brought like many different variables, many different ways for us to analyze that. But we may need to go the extra step at some point to get regional differences within the cornea, and maybe in the edge of the cornea, maybe a little bit in the limbus, a little bit in the sclera, to try to understand how the eye as a whole reacts to a disturbance, either air puff, light, something pressing on it. We'll have to figure out, and I believe we're never doing away with modeling with that. And this is something that I didn't touch base a lot in the lecture because I didn't have time. But we use finite element modeling a lot to get some of these answers. So I think we did a lot of that in the lab.
Thank you very much, Vinicius. We'll move ahead, and BJ Dubs will talk to us a little bit more about the OCT, the optical coherence elastography. I am very excited to see this movement within the cornea. It's a very nice idea, and let's please listen to you. Yeah.
Okay.
Fantastic. I'm still a little slow on the draw with Zoom, but so far I'm doing okay. I just want to thank everybody who's been involved in putting this together. This is what a great opportunity and a great way to start the U.S. Memorial Day weekend. Just a great group of people. Such a pleasure, Vinicius, to see your talk. And thank you all for sending him our way. Carolini Rocha approached me at the Academy one year and said, I know who your next fellow is going to be. And then she introduced me to Vinicius, and she was right. It was a great decision. And I think you can all see that he has a great mind for connecting the basic science and the engineering to the clinical application. And his talk was such a beautiful start to the morning. It's going to make my job a little easier. So with no further ado, thank you again. And I'll just disclose that I do have some intellectual property in in elastography involving OCT and finite element modeling that's held by the Cleveland Clinic. And I do consult for Alcon and Glaukos. Here we go. And there's a long list of people to thank. And right near the top there, you'll see Vinicius's name, along with Andrew Rollins at Case Western, Matt Ford, whose picture you saw, Ibrahim Seven, Brecken Blackbird. These are colleagues who've worked with me over the years to help develop some of these techniques and are helping push them forward now. So as Vinicius mentioned, we have a variety of reasons for being interested in the biomechanics of the cornea that extend all the way to the back of the eye. And Paulo, this maybe goes to your question a little bit. How can we conceptualize what we can't see? And if it weren't for this tight link between corneal structure and biomechanics, I think it would be extremely difficult. Our problem now is that we see the effects of biomechanics after they happen or as they happen. And our goal is to see the effects of biomechanics before they happen. And that's really where this concept of biomechanical measurement becomes so important. As we know, there are two key application areas that we are critically interested in because there's a great need here. One is corneal refractive surgery. And from a global standpoint, this is one of the most frequently performed types of surgery in the world. And the global prevalence of myopia is only increasing, and we believe the demand for this will continue rising as well. So millions and millions of eyes are treated with refractive surgery. At the same time, we have a disease, keratoconus, that we still have difficulty diagnosing in its earliest stages. And we've made a great deal of progress as a field here, but we think there's an opportunity to get to very early diagnosis by finding some of the earliest changes, genetic, biochemical, and biomechanical. And we expect that those changes most likely precede some of the tomographic or morphological changes. And then these two conditions overlap, unfortunately, in the area of postoperative ectasia. And Dr. Ambrosio is a world expert on trying to identify early risk for this. So we'd like to keep these groups separate if we could and find out how to best diagnose them early and assess risk. If we talk about LASIK specifically and generalize that to all photoablative refractive surgery, we know that normal variations in corneal properties can make a difference in outcomes in everyday LASIK practice, even outside of the context of ectasia. This is an example of a simple sensitivity analysis that we did about 10 years ago, looking at corneal stiffness differences in a model. And what we did was simply modeled myopic LASIK for a variety of different magnitudes of myopia. And we used the same corneal geometry and the same eye geometry. All we changed was the stiffness of the cornea. So we changed the elastic modulus parameter and then ran the simulations and looked at the differences in corneal shape after the simulated surgery. And what we saw were very different responses across a range of normal elastic moduli from ex vivo studies of normal human corneas. On the left, we used a high stiffness property from that range. And what we saw was that the corneal displacement actually was somewhat posterior in the central cornea. So the cornea moved backwards ever so slightly after the ablation, along with the shape change from the ablative profile. And so you can imagine a cornea that flattens in the center is going to become, there's going to be an additional myopic correction associated with that, or an overcorrection to some degree. On the other hand, on the right side, we show a weaker cornea that actually shows the opposite effect. Again, with the same surgery, the same geometry, that weaker cornea protrudes forward ever so slightly instead of displacing posteriorly. And what that's going to do is lead to an undercorrection. If we plot this out and show it as a function of intraocular pressure, we can see that number one, it is intraocular pressure dependent, and there is a degree of undercorrection in weaker corneas where the dashed lines are. And I'll try to move my mouse here in case you can see that. This is a 6 diopter attempted LASIK, and the solid line is what was achieved with a stiffer cornea. The dashed line is what was achieved in terms of shape change with the weaker cornea. So this 6 diopter attempt resulted in a 5 diopter correction only. This difference increases as the pressure in the eye goes up. So if we think about the mechanism again with our clinical heads on, we see that increased IOP is going to cause a central cornea that's weaker to protrude even more forward, and we'll get a larger degree of undercorrection. This is a very helpful clinical point to remember, because when we see a patient who comes back to us, let's say a month after LASIK, and they're undercorrected, We're going to, of course, look at our surgical chart and make sure that we program the laser correctly. But we should also be thinking, could this patient have had some occult corneal weakness that we were unable to detect? Is that why they had an undercorrection? Because we have a mechanism that could explain that. So it's very important to follow those patients to stability before we make a decision to retreat or do an enhancement. As we know, enhancement is one of the major risk factors for ectasia. And I think this could be one of the reasons why. We're finding weaker corneas that need enhancements more often. We need to ask the question early and make sure that they're stable. So biomechanical properties do make a difference, even in the realm of normal corneal stiffness values. If we jump to the keratoconus question, there's a period of disease progression that we may miss with our current diagnostic methods because we're measuring shape changes that result from biomechanical changes. And one way to demonstrate this is with another finite element modeling thought exercise here, where we progressively weakened a portion of the cornea and looked at the morphological changes here on the bottom from a normal stiffness value to a modest decrease of 30% to 45% just in one zone of the cornea. And what we can see here is that there's a very slow increase in the apical curvature of the cornea until we get to pretty large amounts of weakening. So, keratoconus doesn't start way up at the top, it's going to start down here. And so this period of silent progression is an opportunity for us to pick up biomechanical weakening maybe before we actually have visual consequences from the disease. As Vinicius mentioned, finite element modeling is a tool for putting some of this information together in simulations. And so we can currently measure everything in yellow here really well. We can measure corneal geometry down to microns. We can produce a finite element mesh that replicates that cornea, and we can simulate our procedures with very high precision. And our lasers are extremely high precision. But what we're missing is this red box here, the material properties. So we don't have patient-specific material properties, and we really don't have spatially resolved patient-specific material properties yet. That really is the goal of much of the work that we and many other groups are working on. I don't need to say much more here. Vinicius made the excellent point that there's a lot of spatial heterogeneity and anisotropy in the cornea. If we look in the lateral dimensions, X and Y, there's the collagen organization that was mentioned. And along with that are these significant differences in cohesive tensile strength from the periphery to the center of the cornea. And interestingly, the central cornea is the weakest in terms of cohesive strength. More interestingly, the inferior portion of the vertical meridian is the weakest. And if we think about where keratoconus tends to present, that's the spot. And so these properties have great relevance to where we see diseases. Also in the axial dimension, the depth-dependent properties, you saw this picture before of 2-photon imaging, and we see along with the structural differences, there are measurable biomechanical differences in this is a compressive modulus where the cornea is being pushed and after it's been separated into 3 different layers. And you can see that there's a much higher resistance to compression in these interwoven anterior parts of the stroma than there are in the deeper portions of the cornea. And this correlates directly to the branching fibril density. So structure and function are very tightly linked, but we don't measure function just by measuring structure. That's why we need to get at the properties. So this is one approach to trying to do this. This is a mock-up of our clinical OCT elastography device. This uses a very high-speed OCT system, not a difficult system to build. Our emphasis isn't on resolution, it's actually on speed of scanning. And so if you saw that granularity in the images Vinicius showed, that's why. We're actually using that graininess, or what we call OCT speckle, as a fiducial marker. So we have an algorithm that tracks that motion in 2 or 3 dimensions, and we can generate a displacement plot for every pixel in the image. So we can tell where that portion of the cornea moved and by what magnitude it moved. So that can give us a displacement for that perturbation. So these maps are showing you, this is an older image with a curved gonio lens. You see the cornea displacing. And at the bottom, we have the same perturbation, but it's tracking the horizontal and the vertical displacements as 2 separate vectors here. And the red means that the cornea is being moved more. So We're measuring some in-plane displacement in the plane of collagen, and we're measuring the axial displacement vertically. And so we started off with this program using those two displacements to learn something about corneal behavior. It's a little bit like a Poisson's modulus. I'm going to mention that because Vinicius brought up the term. We're looking at the ratio of lateral to axial displacement. It's not exactly a Poisson's ratio, but the concept is similar. It's dimensionless. And what we're doing is looking at the vertical meridian is how much the cornea has moved in the lateral direction relative to how much it's moving in the axial direction with that push. And these are edematous eye bank corneas that actually have a large amount of lateral displacement. And then on the far right, the same corneas, after they've been dehydrated to normal thickness and then cross-linked with the standard Dresden protocol, you can see this progression to less and less lateral displacement. So cross-linking actually confers some resistance to lateral strain and probably shear as well. And this is important when we think about the mechanisms of keratoconus. There's an idea that there's a slippage mechanism, Keith Meek described, where the collagen slides apart from itself. And this would probably provide some resistance. This may be part of why cross-linking works to stabilize the condition. And on the right, just to show that we can generate color maps with depth resolved properties, where blue shows us stiffer corneal properties and red shows weaker corneal properties. And even in these rabbit eyes, we can see there's a gradient of weak to or stiff to weak from the front to the back in normal eyes. And then after cross-linking, the entire corneal depth there is stiffer. Now, I want to finish on some clinical data. This is data that Vinicius was really instrumental in helping us to collect and analyze and write up. And so we published a series of papers on normal eyes and then a comparison of normal and keratoconus eyes, all measured with the clinical device. The difference in these measurements is that the clinical system incorporated a force sensor. So as we're applinating the cornea, we're measuring the displacements with OCT in real time, but we are also measuring the force evolution in real time. So now we have a contact force and we have a displacement. And if you've just in your minds flip back to Vinicius's very first slide about measuring mechanical properties, a force and a displacement or a stress and a strain ratio can give you something analogous to a stiffness or a modulus. And so that's what we're doing here. We're calling that value K. We're not going to claim it's exactly the elastic modulus, but it is related to it. And what we can see here is there is a depth-dependent profile in that stiffness value. So we have weaker properties within the epithelium. This blue band here on the bottom left frame is a stiffer anterior stromal region. And then we see it get weaker again towards the deeper part of the cornea. This is a normal cornea that I'm showing. If we take region by region, so we look at a ratio of the anterior stroma to the posterior stroma, it'll give us a metric that compares that depth-dependent property. And so we've used that metric to understand how things change after cross-linking or in keratoconus. And this blue line here is showing the force versus displacement curve in the front of the cornea, and the red is the back of the cornea during the same compression. And you can see that the slope is higher for the anterior cornea. So the slope is really the modulus. So this is telling us the front of the cornea, the anterior stroma is stiffer than the posterior. Now this is a keratoconus cornea, different eye. And what we see here is pretty emblematic of what we see across the board in our keratoconus patients. They've lost that anterior stromal stiffness advantage, at least with this measurement approach. So you can see here the two are collapsed on each other. They're not that different. And in fact, many of the keratoconus patients we measured had a lower anterior stromal stiffness than posterior stiffness, which goes against what a normal cornea looks like. If we think about the histology and what we know about the biochemistry of keratoconus so far, the action really is at the epithelial anterior stromal interface. That's where a lot of the early pathology occurs. That's where we get transverse fibrils start to disappear. All the action is there until you have a hydrops episode. And so it's not surprising to me that the earlier changes of keratoconus might be measurable in the anterior stroma. And just so Renato doesn't get mad at me, I'm going to plant this seed. I think this is consistent with the idea that you would have a posterior elevation change, because what we have here is a more compressible anterior stroma. As the intraocular pressure pushes up against that, you're going to have a dimple in the posterior elevation that will manifest that weakness. So I think that concept is consistent with the idea of early findings on the posterior surface with tomography in this disease. But I think they're ultimately related to this increased compressibility of the anterior stroma. So the third slide on the right is the same keratoconus patient from the middle, but this is 3 months after cross-linking. And look at the marked difference in the slope of the anterior stroma after cross-linking. It's much, much stiffer than it was before. We can also plot by depth. If we just take a cross-section here, we can see that a normal cornea has this peak of stiffness in anterior stroma. The keratoconus cornea here has a much lower and no distinct peak there. There's no strength advantage there. And then after cross-linking in the same eye, a marked increase in the stiffness of the anterior stroma. And these are just a few case-by-case examples of patients that were cross-linked, looking at them 3 months later. And in every case, we see this big difference in the displacement from the front to the back after treatment. So clear evidence of a stiffening effect after cross-linking. LASIK obviously has some effects on this too. And what we see here is a pre-LASIK normal eye, again, stiffer in the anterior stroma. And then after LASIK, 3 months later, we've lost that relative anterior stiffness advantage, because that's precisely where the cornea is weakened. If we look at that as a depth resolve plot here, we see that band of blue stiffness is lost here. And if we plot that by depth, you can see that in the first 100 microns, there's a significant drop in the anterior stiffness, right where the femtosecond flap was made. And then it gradually, as we get deeper in the cornea, returns to normal. Just to step back a bit and to bridge to the other talks that are coming, if we look at 3 different ways of measuring depth-dependent properties, and Dimitri will talk about some of this data probably, the cohesive tensile strength of the cornea from ex vivo studies has showed that early understanding of stronger in the anterior, weaker in the posterior. This is a bunch of different eye bank results plotted together. This is data from a Reunião spectroscopy system that shows a very similar trend, stiffer in the anterior stroma, getting weaker as you go deeper. And then this is an Oct elastography example showing a very similar trend. We have the epithelium in here too. So we're measuring very similar depth-dependent properties with 3 completely different approaches. And I think that's a promising finding, that these things are not in conflict with each other. And the note I want to end on here is, our assumptions about SMILE depend on that normal progression of stiff to weak in the stroma. What we're seeing here in keratoconus patients is that does not necessarily hold true, at least when the disease is manifest. So for patients who are on the spectrum of keratoconus and we're not sure what their properties are, I'm concerned that their anterior stroma may not be stiffer or as stiff as we think it is. And the relative advantage of SMILE may be less than we think. And as we see more and more cases of post-SMILE ectasia, I think it's good for us to think of SMILE very similarly to LASIK in terms of its ectasia risk until we can measure these properties patient by patient. Because in many cases, I think PRK is still going to remain the king for patients who are suspect. And because if we're going to ablate tissue, we'd rather ablate tissue that's not doing a whole lot of work in terms of the mechanics. And I think PRK can help us accomplish that. So this approach involves contact to the cornea. That's a negative. If we could do this without touching the cornea, that would be great. The PhD OCT technique that Vinicius mentioned is an approach to using OCT in a non-contact way. Light is involved and light scatter is the measure. And we are funded for that work right now and just beginning to collect some clinical data in force. So we'll have more to update you with on that later. Right now, we're just measuring the horizontal meridian in 2 dimensions, but we can measure vertical, and we're doing a high-speed approach. Now we're going to extend this to 3 dimensions, which will also allow us to measure displacements in 3 directions. So another point that Vinicius made was there's a directionality to biomechanical properties, and most techniques are measuring it in an A scan in a single dimension. This technique at least has the potential to tell us about shear, about lateral displacements, about axial displacements, and to put those together to give a more comprehensive view of the cornea's behavior. So on that, I'm going to stop and entertain any questions. Thank you so much.
BJ, wonderful work. Congratulations. It's a work of life. and you are doing that for a long time, and you achieved a very, very, very high standard. That's wonderful results and very, very nice technique. Wallace is writing, I don't know if you can see the chat here. So he wrote like a chapter to you. It's 3 questions that you can take an hour to answer each of them. You can choose any of them to answer, or Wallace can pick one and ask directly. You choose. Just trying to help. Yeah, I know.
I hate to disappoint Wallace. Couldn't the difference between anterior and posterior lateral speckle displacement be caused by the difference in the anterior posterior displacement of the different depths? Yes, to your question, it's a really complex deformation that we're applying. You know, we're just trying to applanate the cornea, but it's bending. It's we're changing the tensioning of the collagen fibrils differentially through the cornea. So we think we're actually de-stressing some of the collagen by flattening it. When you take the cornea out of its normal curvature and flatten it, it changes. You actually put some of the fibers under less tension. And so to that end, it's what we're measuring is pretty complex. And so what we've tried to do is do that relative expression of front to back, since the whole cornea is being exposed to the same force, the same perturbation at the same time. But yes, the short answer is it's complicated, and we're trying to model these deformations so that we can extract something closer to true modulus from this applanation.
Mauro, just to give chance to everyone, Wallace.
Good morning, Dr. Dupp. Thank you for being here. And Vinicius, great lecture here at Paulista School of Medicine. We are always very proud of all the professionals we are helping to educate. Dr. Dupp, my questions are very easy to be answered. First is, I do more the biochemistry studies on keratoconus. I'm not on the biomechanics things. I don't have a lab on biomechanics, but a few things that we've been seeing at the lab, and I would like to discuss with you. First is, when we study the distribution of enzymes activity in a keratoconus cornea, we are finding more activity in the areas of ectasia. We don't see, like, for instance, thromboplastins or even metalloproteinase activities. They are not uniform in the entire cornea. It's like niches of activity in the stroma. So I saw your study on the inferior temporal region of the cornea being the weaker part, what is probably proved by our clinical experience, seeing this as the most frequent location for keratoconus, but we are actually not being able to see this in the lab. So many times we see a niche of higher activity in another region and not in that region. And for us, this is very important because may be related with the concept that keratoconus is more a degradation disease than, let's say, slippage disease. This is one thing that I would like you to comment. The second question is even easier than that. The amount of water in the tissue. We've been following UCLA School of Engineering works more recently with this terahertz images sensing of the cornea. Is a process where you can quantify the amount of water in different areas of a single tissue. How do you consider this? If I do a parallel with, let's say, the cartilage of our knees, the main protoglycan in this area is the aggrecan, full of water. So when you have this initial movement of the tissue, this is only relates with the water being displaced. When we see all these, let's say, finite element models or more modern models of the cornea, we don't see any consideration regarding, you know, the substance that is the most prevalent in the tissue. So the two questions is the first, the possibility that we may consider keratoconus being a localized disease and not a diffuse disease in the entire cornea. What makes a little, it's not easy to believe, but it's what we are finding in the lab. And the second thing is, how do you consider water movement in all these cornea deformations?
Those are great questions. And if those are the easy questions, I'd hate to see the hard ones. But I'll start backwards and I'll try to keep it brief, Mauro. Those are great points. The proteoglycans are such an important part of the overall, you know, elastic and viscoelastic behavior of the cornea. And we're taking a fairly dumb approach to the measurement. We just, you know, we're looking at all the ingredients interacting together in vivo under physiologic conditions. And it's going to be some complex interaction of the water distribution. We, from a modeling standpoint, we have started to include some poroelastic elements into the model to account for this. But for these measurements, which last about 2 to 3 seconds, we're simply making the assumption that there's not a lot of time for water redistribution on such a short time scale. And I'm sure that's not completely correct, but it's a simplifying assumption that we're using in our current back calculations to get properties. But to your point, that's a really important thing to incorporate, especially for looking at disease progression, where these changes occur over years and not seconds. And then to the first question, I think your observation is right on. This idea of keratoconus being a somewhat having a localized origin. Most of the work I've seen too, and I want to do some more reading about what you're doing, does point to this idea that you can spatially localize some of these biochemical differences. And I think it probably starts at a foci, and then there's this cycle of degradation that occurs with mechanical feedback and other factors that just, you know, and eye rubbing, add all that together. And I think we have a local disease that becomes less local as it progresses. So thanks for some great points.
Thank you very, very much, BJ. Mauro, you can, yeah, thank you. Otherwise, we'll just get messy. My role here is to keep the time constrained. Otherwise, Felipe will just yell at me. And we'll move on to Dimitri Cherniak. In fact, the Wallace spot, Ron Kruger, that's in the audience. Ron, welcome. We have you here. You're an idol for all of us. You welcome all fellows from Brazil within yourself. And I guess we can have Ron answering the question after Dimitri's presentation. That way we will have time to read that. And it's related to Brazil also. Dimitri, yours.
Thank you so much, Paula. It's a pleasure to be in such a distinguished company. And I thoroughly enjoyed the previous presentations, which I think create wonderful foundation for what I'm about to talk about. So thank you again for having me. And hopefully you can all see me and the screen. So today I'll talk a little bit more about Brouillon spectroscopy, a technique that was mentioned in the 2 previous presentations. And it's basically getting to the point where it is being commercialized. So I'd like to show you this instrument, which we call Brouillon Optical Scanner System, or BOSS for short. And right now we're going into the clinical studies for FDA. So it's what you see is actually a machine that we build several of, and they're used for clinical research. How does it work? So we have a light source which is held at very precise frequency, and we look at how this light interacts with tissue using a what we call patient interface. with objective lens that focuses the light into various localized volumes of space in the cornea and in the lens. And then the signal that comes back gets analyzed by a fairly sophisticated spectrometer that can measure the minute frequency changes that happened due to light interacting on, as was again explained in some of the earlier talks. There is a very nice animation that was built by our marketing partners that you can see on our website, which talks a little bit more about how it works and how we construct maps. And what are the substantial advantages of Brillouin's system compared to some of the other equipment that's available on the market? So the big advantages are it's a real-time, non-contact, high-resolution, localized way to directly measure and image living tissues. So it's kind of a OCT on steroids, if you want to think about it that way, that allows you to measure at least one component of elasticity, which is the longitudinal modulus, as well as assess viscosity. So we all know that sometimes looks can be deceiving. I mean, the rubber tiles in the children's playground may look the same as the tiles in somebody's kitchen, but some of them are made of stone, some of them are made of rubber, which have very different elastic properties. So if somebody falls down, it makes a huge difference. Similarly, for viscosity, certain fluids may look the same, but they have very different properties, such as water versus oil or honey. And this is another important factor that was, again, mentioned earlier, that viscoelastic properties is kind of one of the critical elements of biomechanical assessment. One way to understand also what Brillouin imaging does is to compare images of this mouse embryo. It's the same embryo measured by OCT and measured by Brillouin imaging. So you can see that OCT gives you very good information about morphology and shapes, but it doesn't really show you any differences in structural information for this embryo. And when you look at the Brillouin image, you can see that there are certain areas that are substantially stiffer in their elastic properties, such as the hard tissue of this developing embryo, versus some of the neural structures that are softer. So this is like another dimension that was not previously accessible to clinical research, and it reveals structural differences beyond morphological differences. So how does it compare with some of the other techniques? I think I'm not going to dwell on this slide because there was excellent overview by Vinicius and by BJ as to what are the available techniques. But where we see advantages that it's a direct localized measurements. So some of the other techniques like air puff tonometry require certain modeling to be in place in order to deduce the actual biomechanical properties from sort of all this information that's being provided. Whereas with Brillouin spectroscopy, basically you get spectral shift, which provides a one-to-one mapping into the elastic value that's measured in gigapascals. Again, I'm not going to dwell on the unmet needs. The first generation of BOSS instrument can address anterior segment, so we're measuring lens and the cornea, but there are also opportunities to go deeper into the eye, and biomechanics plays huge role in glaucoma and potentially other applications such as high myopia and scleral changes with progressive myopia. And initial applications, as I mentioned, are on the anterior segment, and there's no shortage of clinical areas that can substantially benefit in terms of screening and in terms of surgical planning, where biomechanical material properties can refine the treatment plans and also identify which individuals should or should not get certain type of procedure. In my days in Visex, almost every clinical studies that we've done had some unusual outliers that could not be attributed to either the laser or the diagnostic. And that made me a firm believer that there's something about biomechanical properties that are fairly unique to each individual, and you can't do sort of the best service for each person without understanding that biological variability. So let me give you a little bit of an overview of what type of data the system generates. So this is an example of pentacam images of a keratoconic patient where you see sagittal curvature and thickness maps from pentacam. And the outline indicates the region that was measured in fairly high level of detail by the Brouillon spectroscopy. So you can see that the area of local thinning, or sort of the area that's the thinnest as shown in the pentacam, is actually the area that shows fairly substantial focal weakening in the color maps that are very similar to what you would see in sort of topographic or tomographic maps. So right now, this was done by an earlier instrument, and unfortunately, Corona pandemic has sort of set us a little bit behind in clinical research, given the restrictions for elective procedures and clinical studies. But as I said, we're quickly catching up. 5 of our machines are at various clinical sites, including the study that we're doing for FDA, which is repeatability and reproducibility. To summarize some of the studies that were already completed using a prototype machine, or studies around repeatability in cornea and lens at Mass General Hospital and Mass Pioneer, studies with Dr. Seiler and IROC, a couple of studies in Korea at St. Mary's Hospital, as well as First Clinic around refractive surgery and cataract surgery. And then the study I'll mention, which was one of the most recent studies that was done, is studied with Dr. Stolting at Wolfson Eye Institute in Atlanta, where we used subjects that had keratoconus, and they undergone epi-on cross-linking procedure. We're doing multiple studies right now. These are some of the sites that are either already online or about to get online using the actual BOSS instrument rather than the prototype system. So I'm hoping in the next 6 to 12 months, we'll have a lot more data to share with you using the actual commercial version of the machine. So just to briefly give you information about the clinical setup, and the commercial machine has very similar characteristics in terms of laser power. We were able to shorten the integration time now to 2.1 milliseconds, 2.1 second, I'm sorry, so that the exam acquisition time is faster and highly automated. So the idea is to use near-infrared laser to create a focal region inside a tissue from where we collect Brouillon signal, and we can compile the data from an axial scan to understand the Brouillon shift in terms of frequency within the tissue. We use eye tracker to register the data to a specific location on the eye, and then that allows us to generate maps. So the early system operated in sort of units of frequency, but now we display data in Pascals, which is the true longitudinal elastic modulus. Here's some representative images that were collected from the study at the Wolfson Eye Institute, where we have pre-op and post-op measurements on the same eye before and after the cross-linking procedure. And you can see there's overall stiffening of the tissue across the board as a result of the procedure. And the amount of stiffening varies from one individual to another, but also from one location to another, which is one of the interesting observations that we've seen, where we see overall increase in mean corneal stiffness after the procedure, as well as reduced heterogeneity that we measured from those subjects. So it was interesting to see that the regional difference has been reduced by almost a factor of 2, whereas the Kmax values, which is kind of the gold standard indicator of the change, have not really changed substantially as the result of the procedure. So again, this is just a snippet of data. And as I said, there's more data to come as we explore other indications, particularly refractive surgery and other ones. Refractive surgery, while being sort of one of the most commonly used surgical procedure, is still far from perfect. And today we have an arsenal of tools that allow physicians to make decisions around whether to treat and not to treat, or how to treat. And there's obviously things like patient needs, refraction, there's wavefront, topography, tomography, photometry. But what we hope to do is to add this another dimension that potentially can substantially improve this decision process that shows you kind of the spectrum of biomechanical values. And what we've seen that even normal corneas may be on the different sides of the spectrum. So perhaps, as BJ mentioned, there might be a nomogram adjustment that can be developed to improve the outcomes of the refractive procedure. So in conclusion, Berlin spectroscopy allows you to create a 3-dimensional biomechanical mapping and shows potential for improved diagnostic and surgical planning capabilities in refractive, cataract, and cross-linking procedures. And I believe there is more applications to follow as we get this instrument into the hands of physicians, and hopefully there's a lot of clinical research that can be done to uncover those applications in the future. So thank you very much, and I'll stop at that point.
Dimitri, brilliant talk as always. We are fans of you. You know that from your time here in Brazil with physics and all the work you did. And well, Intelon is doing very well. I want to take advantage on my role as a chairman here to ask you about the sclera. I'm very interested in the sclera itself to allow me to tell the patients which patients should be treated with like atropine to avoid progressive myopia, and to tell the patients when the myopia will be stable, or to tell the parents what will be the final myopia of that kid. What working are you doing there?
So there was some feasibility work done in measuring sclera at Mass General Hospital, and we still have a sponsored research agreement. So we kind of collaborate on some of the technological improvements that are being done. For sclera, in order to be able to get measurements from non-transparent tissues, there's additional filtering that has to take place so that we don't overwhelm the Berlin signal with sort of all the noise coming from the sort of just reflections and scatter of the non-transparent tissue. However, one of the projects that is very well on the way is to add what we call a rubidium gas filter to the system, which is able to filter out some of that scatter. And we have shown ex vivo measurements of porcine sclera that are fairly repeatable and reproducible. Obviously, with current system, we can only access maybe sort of equatorial region of sclera. So there has to be some inference as to whether equatorial scleral properties directly correlate to the sort of posterior region, which is typically held responsible for weakening in the progressive myopia. But this is also one of the areas that we have very strong interest in view of such sort of worldwide pandemic of progressive myopia, especially in Asia. So we're actively pursuing that as well.
Fantastic. I'm sure you'll be able to place any kind of super lens and see through the eye and through the retina that we don't care, and it's transparent, and then access the posterior pole or something like that. But Wallace already asked for our data, and I echo him asking for allow offering ourselves to help you, and you know we are very close and we will cooperate even more. I want to ask Ron Kruger, if Ron is there, to answer Wallace's question. Ron, are you available? Can you listen to us? I think Ron is listening. So we will take questions, and we are also behind schedule. Yeah, you don't think he's online right now. And move on to Renato. So Renato is a very good friend. He doesn't need presentations. President of the ISRS, as Felipe told, very close to us. He's a professor of our postgraduate course here. Wallace is asking, brilliant, is influenced by intraocular pressure. So Renato, you need to wait for a little bit because Wallace is one that wants to ask questions. And thanks God. Dimitri.
This is an area of active research, but I'd say my answer would be yes. There is an impact because obviously intraocular pressure puts more force on the corneal tissue, and I would mention the rest of the differences. Right now we have more data for crystalline lens actually than for the cornea, because we're doing a single scan where we can see the Berlin signal in aqueous as well as in vitreous. So there may be some additional information that we can obtain by looking at the correlation between intraocular pressure and the three signals from lens, vitreous, and aqueous that would allow us to take that into account. So this is an area of active clinical evaluation for us.
Thank you, Dimitri. Renato, stage is yours.
Thank you very much. It's a huge pleasure and honor to participate in this great meeting. Excellent talks by Dimitri. Actually, the question by Wallace is exactly one of the questions I would have to Dimitri regarding the IOP and the impact on the corneal measurements. When we think about, I think it's a little frozen here, the corneal biomechanics, I would say that I have been working with corneal biomechanics for over 15 years in the clinical setting, and it's been a fundamental part of my multimodal imaging. Of course, I have some financial disclosures, including Oculus, but I will start with this quote that we know that we need to know more. All we know is that as much as we have more experience, more knowledge, we have the conscience that we need to know more. And why do we care about biomechanics? Great talks by Vinicius and BJ and Dimitri. We need to know more about IOP measurements because the cornea influence the IOP measurements, but also the cornea can give you some prognosis for glaucoma neuropathy. In terms of corneal disease, edema, and ectasia, and of course, refractive surgery is far from being perfect, as beautifully said by Dimitri, who has a long experience with many trials for all the generations on the excimer laser. We have never been as good as, but corneal biomechanics can help us to understand the predictability and improving on the accuracy and also safety for avoiding aberrations like the spherical aberration induction, and also the most feared complication, which is ectasia. We have multimodal corneal imaging for understanding diagnosis, prognosis, staging, detailed follow-up, patient education. And I would say that biomechanics is the major part on this as it is today because of the concept that everything starts on the change on the modulus of elasticity. We have increase in strain, focal thinning would come, and then all the aberrations. And I really like the concept from BJ that everything would be related to the change on the compressibility on the front surface, and you have the epithelium, and you have now the ability to look at the epithelium in a detailed fashion. So all of this will be secondary changes to corneal structural biomechanical change. And every cornea can undergo ectasia, and we are close to the Violet June campaign, and I invite all of you to participate, to tell people about keratoconus. And the major message is telling people not to rub the eye because it can aggravate keratoconus and cause ectasia. And any cornea may undergo ectasia if you have enough biomechanical impact from the environment. And of course, laser vision correction do weaken the cornea, and I like the quote by BJ that SMILE does a little less impact than LASIK, but eventually not so much less. And PRK is still the king. I agree that, and eventually phakic IOLs is also here to be considered. So when we think about biomechanical properties, it comes with the biological properties. I would say this is related to wound healing, and my good friend Canrobel Oliveira quote that this is an old exam that never existed since the old times of the RK. But we started doing biomechanical measurement in the clinical setting with the ORA that was introduced in the ESCRS in 2005 by our past good friend David Luce, with the concept of hysteresis, and we start learning a lot from corneal biomechanical understanding. We have this very nice paper from the JCRS, which has over 1,400 citations, with the understanding of the biomechanical in this clinical setting. You saw the beautiful talk by Vinicius with the destructive tests that we do in the lab with stress for characterizing stress strain, but we need to do that in the clinical setting. So we start studying with the ORA, and the nice thesis by Bruno Fontes that got the Trautmann Award. We have a very nice example here of 9.1 of corneal hysteresis, but with a different waveform signal from another 9.1 hysteresis cornea. This is a thin cornea that is normal. This is a patient with mild keratoconus. And eventually learning about this waveform was the continuation of the work done by Alan Luz, who also did a beautiful work at the Unifesp PhD thesis. So we have also the understanding that tomography can be integrated to biomechanics, and this was the first logo of our group that combined corneal biomechanics with the ORA and Pentacam shine fluid imaging. And they published some reports on that, including this case that did not have surgery in the right eye and had ectasia in the left eye after LASIK. And you would see some susceptibility on tomography, borderline values on tomography and biomechanics. In 2009, I was introduced to the shine fluid dynamic system that takes 140 frames in 31 milliseconds, the Corvus, and we start doing some work. This was the publication we published on the Brazilian Journal of Ophthalmology that summarizes the deformation response, and also we have to see that the change of the movement of the whole eye. So we have a whole eye movement that may also imply the biomechanics of the sclera and the orbit fat. We have a study on contact lens experiment that we mounted on anterior chamber, and here we can beautifully see the impact from the pressures, not IOPs, the pressure inside of the chamber on this corneal models on the contact lens, and the strongest lens will deform less. But if you consider a lower pressure and the pliable lens here in a higher pressure, you'd see that this system is stiffer than this system. So IOP makes a huge impact. And understanding IOP, we have many situations, like this published case on the PISK, pressure-induced stromal keratitis. The patient was treated by a colleague of ours after LASIK as DLK, and the pressure was 53. And I asked him when he called me, how is the pressure? Is 12. I measured the pressure 12 with Goldman. And I did the diagnosis by the phone. Please send the patient here. And we saw the patient very, very high pressure. And after decreasing the pressure, you see a dramatic change on corneal shape and also the deformation response that you can see after the decrease. So IOP has a bidirectional influence. When we see this deformation of a keratoconic cornea and a strong cornea with a patient with a normal strong cornea, we have to consider IOP, and we have the biomechanically compensated IOP based on finite element models by the El Sheikh Ahmed's group. And this is going to be combined with many of deformation velocity, deformation amplitude, and increasing concave radius for the CBI, which was published by Ricardo and got also the Trautmann Award a few years later. And here we can see a soft cornea and a strong cornea nicely drawn here that you have a different deformation response, but you have to understand IOP to understand the corneal deformation. We have the CBI post-LVC after LASIK. In many cases of LASIK would have a high CBI, but if you have a different algorithm of post-LVC, this would be very nice and specific for saying this is a stable post-LVC, post-laser vision correction, but still sensitive to detect ectasia after laser vision correction. Our concept is to integrate tomography and biomechanics, and we have done that with artificial intelligence. Very nice work by Bernardo Lopez in his thesis. And this is the summary of the JRS 2017 publication, in which we have a very nice separation, I would say virtually perfect separation for the clinical ectasia cases, and with a different threshold, we can improve the sensitivity in the very asymmetric ectasia cases with the normal topography based on strict criteria. And this is, in our opinion, is a surrogate or a epitomize of corneal biomechanical susceptibility. And the case that we published in 2010 is still stable with 2015. She would be very abnormal on the integrated tomography and biomechanical value that is easy to understand the separation. Biomechanical susceptibility or foam fruits can then be identified in both eyes of the same patient, and this is the best model that I can show you. This identical twin sister with both eyes normal topography. All eyes had a normal TBI. They were considered confirmed to be twins, identical twins based on genetic profile, and some of the genetic understanding from the AVA gene, that is a new keratoconus test on the genetic profile by Avellino, would identify mild susceptibility for keratoconus, which I think it's going to be the future for this. We have some studies that looked at the TBI with a lower sensitivity than our published paper. And now I come with another quote that sometimes we know a little bit and we think we are right, and we need to know much more to know we are wrong. And I would say it's not a matter of being wrong, it's a matter of having to know more. And we have the ability to have a continuous evolution in this revolution on artificial intelligence biomechanical measurements, in which we increase the number of patients with 505.1 in a multi-center study, and we increase the algorithms with the brain. Very nice work by Edileuza Leão, and also Aidono Machado and Bernardo Lopes and João Marcelo Lila collaborated with this so that we can improve about 10% of the sensitivity of the new algorithm for detecting the mild cases. When I see cases like this down here, I would say maybe those cases are the unilateral ectasia cases, not keratoconus, but unilateral ectasia due to biomechanical properties. And when I see cases normal that are up here, I would say those are the susceptible cases. And we may merge I love the concept from B.J. Dupes on the deterministic and probabilistic ideas with the work that is done by Abhijit Sinta Roy, who had learned a lot from B.J.'s lab in the past, who has a software that can integrate the tomography and biomechanics and have a finite element model that inversely could say how the cornea will be after laser vision correction procedures. So I think that tomography and biomechanics are fundamental for us in this multimodal approach. Corneal biomechanics is going to evolve to ocular biomechanics. I would say susceptibility is the future for understanding glaucoma as well, not only understanding the correct pressure, but we have to understand susceptibility for ectasia and giving more treatments for keratoconus. This is a path for individualized medicine, and individualized medicine would compute the data from the patient that we have with some finite element models and other models that we can create on the computer to simulate what's going to happen, like the beautiful work that was seen at the Academy of Medical in Brazil that Paulo Shore participated a couple of weeks ago, that merged artificial intelligence with medicine and just beyond ophthalmology. So this is a matter of doing the best for the patient and eventually not doing harm before anything else. So how I do use the TBI in my clinical practice, I use it as a major point to identify if the cornea can be weakened by surface ablation or femtolasic and SMILE. And I agree that femtolasic and SMILE don't have much difference, but SMILE may have some other advantages considering dry eye and also patient understanding. Of course, phakic IOL, like the IQ phakic and the ICL, will be very much important for cases considering the level of correction, the susceptibility, and eventually the patient has a disease, an ectatic disease, and the patient is a therapeutic domain. This is an honor to participate in this group, and I invite all of you to participate and collaborate with the Violet June campaign that's starting next week. Thank you very much for the opportunity, and I look forward to very nice discussions. And again, it's an honor to participate with you in this webinar and to be part of the Unifesp family for helping people to be the best ophthalmologists as possible.
We are indeed a very big family, Renato. That's very nice to hear from you, and especially from your connections with everyone here in the audience. Yes, amazing lectures. as Pablo said. We don't have more time, but Felipe said we can go forward, and so I will leave our guests free if you can stay. Thank you very much to stay. But if you need to leave, we will understand. We will just expand the discussion a little bit more. It's very rare to have all of you in the same place with ourselves in a situation that is non-formal, but it's a very deep, it's a discussion that is being held in a very deep level. I myself have a set of questions, but I want to start with one. That's something that BJ mentioned, and I argue with Renato every time. That's about the posterior surface of the cornea. Wallace is also involved in this discussion as Mauro, and I want to get back to BJ and start asking you, why are not we seeing or paying attention, or in fact, are we not seeing or are we not paying attention to the posterior surface of the cornea? My challenge once was, why don't we go to a meeting and just show the posterior surface of the cornea? At least we'll get used to it, and we'll be able to understand how to analyze it, because the anterior surface is straightforward. We know that for decades. It's very easy for us to say, well, it's maybe normal, but maybe not normal. We have tough guys that will say every time not normal, but not the posterior. Why?
I think that's a great question, Paulo, and I don't have an easy answer, but I think one reason we're a bit behind on posterior surface analysis is because it still is a difficult layer to measure accurately. You know, the refractive index going from the corneal stroma to the aqueous is so small that edge detection algorithms really struggle to get it right. And we don't have that problem on the anterior surface. We've got a big refractive index that makes edge detection algorithms just work so much better. So I think there's that component. And although I think it's been largely overcome, it put that part of the field behind 20 or 30 years compared to anterior surface analysis. And then the other part of it is that, you know, the technology to measure that's more expensive. And so, you know, optometry offices generally don't have a tomography device because it's, you know, it's much more expensive, and you can get a topographer for less than $10,000 US. So in the general community that's referring patients in, most of those people aren't seeing the posterior surface at all. So there's just a big knowledge gap that I think we need to bridge. That's really important. I'm sure Renato has thoughts on that too.
Yeah, I'm sure he's willing to jump in.
I would just add on the refractive index that we don't see the posterior float. We cannot see it because the front surface changes. So it's like if you stick a pencil in a water cup, you see, if you bend it, you see the pencil broken. So you have to compensate for that. And we don't know exactly how to do this compensation. So even though we know we have to compensate and we have a lot of algorithms for compensating it, it's not the same as looking at the first reflection of the front surface. So we have limitations, and I firmly believe that combining technology is the key. Combining technologies is like combining strengths. So if you have Scheinflug with a wavelength of a blue light and you have the infrared from OCT together, we may be able to enhance our understanding. But again, you go for the second point that you made, cost will be an issue because it will be much more expensive than what we have today.
Vinicius, I would love to hear yourself in this issue.
Yeah, well, Dr. Dupes and Dr. Ambrosio already mentioned major issues. I believe that, as Dr. Ambrosio said, like if OCT wasn't that much expensive, like if we had more availability of OCT to more widespread use of OCT and even more knowledge on what it can produce, I think we would probably be imaging the posterior cornea a little bit better. And I think that's one of the reasons. I remember even like when I was a fellow there discussing posterior cornea with with Wallace and like saying like, yeah, it's the theory is there, it's very good, but there's still a lot of noise. There's still a lot of situations where the posterior cornea is not well read. So I believe if we start to do more studies regarding OCT technology to see the cornea, we would probably have more, or combining technologies, as Dr. Ambrosio said, like we would definitely have more data and more reliable data to see, to measure the posterior cornea a little bit better.
And Dimitri, I remember we chatting about the focusing or the depth control you can have in brilliant. Can you measure, or do you have any insight on the posterior surface of the cornea, because you show a whole map of the cornea?
We do provide axial scans. So for each of the points that we show on the map, you can actually click on and see the axial profile of the measurements that we take, which I think potentially can help in the future to look at, for example, demarcation lines from cross-linking, or to see in the focal weakening area where this weakness comes from, whether it's anterior or posterior. However, at this point, I don't know if the resolution of our machine is even comparable with OCT. There's also eye movements that are happening because the acquisition time is somewhat longer than what you have with A scans. But I think in the future, there will be more ability to basically get reliable pachymetry from those axial scans, as well as get more detailed biomechanical information as you go through the depth of the tissue. So ex vivo data that Juliana Scarcelli have shown is very detailed, but in vivo, obviously, it's a little bit more complex with eye movements and other factors influencing accuracy.
Yeah, thank you all of you. Mauro has a question, and then we have Renato and some questions left from Wallace.
Thank you, Paulo. Last question to you all. Actually, in a current clinical examination, every time we place a patient at the slit lamp, patient tends to move the head backwards. So we are always using the other hand to keep the patient in the exact position. So the patient won't move from, like, say, the tonometer. I would like to, this is a very basic question. How are you managing the position of the eye inside the orbit first, and consider the entire structure being over the neck? Is this patient moving the head at all? And this can affect the measurements. And have you tried to measure patients, suppose, with Graves' disease before and after taking out all the, let's say, the tissue from the orbit, to see if there is any difference in all these measurements?
Mara, I'll make a quick comment. That's a big problem, as Dimitri suggested. Patient motion is an important confounder. So with our OCE device, we actually have a bite bar, and we have a Ziploc bag. That's our elegant disposable that we use. And the patient bites on this block, and it really can stabilize, the skeleton pretty well. The skull doesn't move. We found that's more helpful than actually a headrest, because patients can still move around. Yep. Vinicius has bitten that bite bar many times himself.
Yep. we actually did some pilot like work with that, and we analyzed the difference between like just having the head bar and the bite plate. And the bite plate not only has more like stability, but also the image, because of the stability, the image quality gets better as well. So and even if you, I think I can comment on the OCE part. Because everything, if you consider that the head's moving, as long as it's not a big movement, and we are tracking motion within the cornea, and we are comparing that motion within the anterior and the posterior cornea, even if everything moves, you're still kind of measuring the same distance. It would be very hard for a small head movement to cause a lot of changes in that measurement, because in the end, we're measuring a relative distance. when I was there, that's what we did. But the acquisition time wasn't big, and the bite plate stabilized things to the point where the image quality and the acquisition times were much more efficient. I can comment on really one, never worked that. And we know that the corvis, when the air puff hits, there is some motion of the eye as well. But as Dr. Ambrosio said, like they have many algorithms and many mathematical derivations that they can do to fix for that. So, but it is a problem. It's a great idea actually to measure Graves patients maybe during the active phase of the disease and the quiescent phase of the disease. That's actually a great idea. I never thought of that. Yeah, that's definitely something that could be done.
Thank you. Dimitri, we have a question for you from Renato. May you comment on how long it takes for standard exam? And Ron said, great discussions and great talk. Thank you, Ron.
So the timing is depends on sort of how detailed of a scan that you want to obtain. Right now, as I mentioned, a single volume measurement takes about 0.1 second. So an axial scan will take maybe 2 to 3 seconds through the depth of cornea to get reasonable sort of resolution. But the positions on the cornea would really dictate sort of the overall time of the exam. Typically, we measure about 15 to 20 points in certain sort of spatial pattern. You may want to measure more for the keratoconus to get a little bit more detailed spatial information in the keratoconus region. But at this point, a typical scan takes probably about a couple of minutes, including positioning the patient and kind of doing pre-scan to localize the distance to the cornea that enables more detailed measurements after that. As we sort of get more sophisticated cameras that allow us to have lower integration time, then that will directly translate into the overall sort of time at the instrument. But right now, I would say it's about probably a couple of minutes per eye.
Thank you. And I will break the protocol and ask Ron. Hi, Ron.
Follow.
Very nice to see you here.
Yes, a great meeting. I enjoyed listening. I actually had another conference that we were hosting that I was sort of just moderating. So I kind of had to do both at the same time, which was difficult. But I just had a quick comment. Rohit Shetty and myself and Brad Randleman published a paper about a year or so ago where there was a SMILE patient who had normal tomography, normal corvis measurements, and underwent SMILE for a high correction and then developed ectasia later. And he saved a tissue and then decided to grab that tissue and analyze it biochemically, and was able to find out that especially the eye that had the most ectasia had more significantly less lysyl oxidase within it. And that's a natural cross-linker in the cornea. So when we're drilling down from seeing keratoconus to the naked eye, to seeing it on topography, to seeing it on tomography, to seeing it with biomechanical measurements, to actually maybe seeing it biochemically, can we drill this thing down further and further to the point where we can come up with tests that are not just, elasticity tests, but maybe even biochemical tests?
If I may, Ron, excellent point. I know this case very well, and everything is not very normal. If I show this case for Edson Mori criteria, he would say that the topography is suspicious. But of course, knowing that the case had ectasia, you see abnormalities in every case. So the specificity will be 0. You don't do surgery in almost anyone. But you made a brilliant point, which is the integration of data going towards shape and structure for the genetics and the molecular biology domain. Thank you very much. It's good to see you.
Yeah, good to see you too. Great talks. I wonder, is this going to be a recorded session that we can play it back at some later time?
Yeah. Yeah, it's being recorded. And I thank you very much for the comment, Ron. I think we finished with from the place we start. And I was thinking about, well, what are we trying to show? What are we trying to achieve? That is the patient's health. So it's mostly which patients will be safely operated. And we can use any kind of machine we want, any tool we want. The idea is not that the tool is the focus. So the focus is the patient. And you are showing that you concluded that in a very, very nice style. Mauro also pointed that biochemistry is very important to take part of that multimodal diagnosis. It's not just multimodal image diagnosis, it's a multimodal diagnosis. And I'm sure that will be integrated in some kind of IA machine. We'll probably put more things there, behavior of the patient, family, and the genetic tests, and so on. So we have lots of data. We need to make the right questions. And I will summarize, Felipe. In fact, you will summarize. Close the session, please.
Well, thank you. I would like to summarize this by saying that, as pointed out previously, the patient is our aim, and thinking about that we have had the idea to line up all these top experts in this subject so that we can share information and advance in these discussions. I know it's a hard topic for most of our colleagues, and such sessions I feel they contribute to our ophthalmology practice in getting to know these multimodal diagnostics, as Dr. Paulo and Dr. Mauro and all these speakers have told before. So I'd like once again to thank you all for the participation, and as well as our attendees that are listening to us up to this time. And I apologize for being a little late on schedule. And once again, thank you very much. And I hope you all have had joy in discussing these matters. And it's up to, like Dr. William said, if you want to continue talking about this, please, we need to. You can take all day long. I'm just gonna close this meeting, but it's an opportunity for all of us to get involved in this matter more and more and more. So thank you once again. This was a wonderful session, and I hope everyone has a really nice weekend, a really nice week, and thank you all again.
Great day.
Bye.
See you all in person sometime soon.
Thank you. Looking forward to it.
All right. Bye.
Yeah, we must repeat, as Dr. Professor Shimon said now in the chat.
Congratulations to all. Thank you very much for being here. We learned a lot from you, as always. Hi, Ron. Good to see you.
Great to see you too, Walsey.
Bye.
We have to meet in person, you know.
I know.
Can't handle that anymore. Bye. Bye.
All right.